Okay, students, let's look now at Chapter 7 problems. So Chapter 7, pages 237 through 240. All right, so let's look at number 5. Okay. It says the Earth's radius is about 4,000 miles. Okay, so this is number 5. So let's draw the Earth. So its radius is 5,000 miles. Okay. All right. Kampala, the capital of Uganda, and Singapore are both nearly on the equator. The distance between them is 5,000 miles. Okay, so maybe I should have drawn it a little different than this. Let me do this. Let's redraw it. Okay, so here's the center. We're going to pretend that we're looking, no, let me do this. Chapter 7, pages 237 to 240. I'm sorry. Number 5. All right, I don't know if I can do a 3D Earth or not. All right, the radius, let's just do something like this right here. Something like that. Here's the center. Okay, here's one city. That's the equator. And this is Singapore. Okay, whoops, that's Singapore right there. So that's Kampala, and that's Singapore. Okay. All right. And the distance, so the radius is 5,000 miles. And then the distance between, or let's say this, let's write it as S, not D, S. The distance between them is, I'm writing everything backwards. I'm sorry. That's 4,000. The distance between them is 5,000, correct? Yeah. Okay, so it says what? Through what angle do you turn relative to the Earth if you fly from Kampala to Singapore? Give your answer in both degrees and radians. Okay. All right, well, if you remember how to find theta, to find the angle or the arc in radians, okay, we know that theta in radians is equal to the arc distance divided by the radius, okay? And so the arc distance is 5,000 miles, and the radius is 4,000 miles. So we get what? Well, 4,000 divided by 5,000 should be right at 1.25, right? 5,000 divided by, well, my calculator worked, 5,000 divided by 4,000 is 1.25, exactly. It should be one. Boy, I can't write anything right today. I guess because it's the end of the week. It's Thursday. All right, 1.25 radians, okay? So there it is in radians, all right? Now let's find it in degrees. Well, if you remember, we know that that radians is what? That 2 pi radians is 360 degrees. So 1.25 radians times 360 degrees divided by 2 pi. Now you could actually reduce this, make that 1 and make that 180. You could do that. That'd be fine. And so what do we get? We get what? We get 1.25 times 360 divided by 2 times, and you have to use pi, and you get 71.6 degrees. Okay, so there it is in degrees and radians. And then the second part says what? The flight from Kampala to Singapore takes 9 hours. What are the plane's angular speed relative to the Earth? Well, if you remember, let's go to part B. If you remember, this is number 5, part B. Okay. Did I skip a slide? Yeah, I did. Number 5, part B. This is 5B. Go ahead and label it. Come on now. Right. All right, so we can find angular speed by doing what? By taking the change in theta over the change in time. Well, we know that theta was 1.25 radians, and the time is 9 hours, so that would be what? 1.25 divided by 9, and we get, that's not right. 1.25 divided by, well, my calculator don't want to work. Divided by 9 is 0.139, we're going to round it up, radians per hour, okay? All right, good, okay? And, of course, we can convert that to radians per second, but does it ask us to do that? Angular speed, that's typically how we do it. So we say 1.39 radians per hour, and we know that 1 hour, is what? Well, 1 hour is 3,600 seconds. So we get a really small answer, don't we? So we get 0.139 divided by 3,600, and we get 3.86 times 10 to the negative 5th radians per second. So it's not very much, is it? Not very much turn. Okay? All right, let's move on to another problem. Let's go to a clean slide. Let's look now at number, I think, 21. Yeah, number 21. All right, it says, what is the net torque about the axle on the pulley in figure 7.21. All right, so we've got number 21. We're still on chapter 7. We've got a wheel like this. The distance all the way across is 4 centimeters, which we need the radius, don't we? That is actually what in meters? So the diameter is 0.04 meters, right? Which makes the radius 0.02 meters, correct? Okay, it should be correct. All right. We've got to have the radius. And it's wanting to know what is the net torque. Well, now we know we can calculate torque by using what equation? Well, we know that tau, which is torque, is equal to the force times the radius sine of theta. And I let my formula get in the way of the drawing, so let's redraw it right over here. All right, so we got a radius of 0.02 meters. And we got a force going this way, and that one's 20 newtons. That's a force. Let's say that's F1. And then we got a force going this way, and this is F2, and it is 30 newtons. Okay. All right, now we need to remember the right-hand rule when we're talking about torque. Okay, so this rope's pulling this way, which causes the rotation. If you pull down, here it's rotating this way, right, on this force. That's counterclockwise rotation, so that makes torque then, torque would be positive over here on this side, wouldn't it? Well, we have a 30 Newton force over here on this side, and the rotation is this way, so that's clockwise rotation, and that means that torque then and angular speed is going to be negative. Torque is negative on that side. So, having said and done all that, then we can sum up the torques, can't we? We sure can, because it asks for what? What is the net torque? Yeah, what is the net torque? So the sum of all torques then is equal to torque 1 plus torque 2, isn't it? Sure it is. That's tau, by the way. So let's sum them up. So sum of all torques are the net torque. So torque net is equal to, well, torque 1 is what? Okay. Well, let's see. The force is what? 20 newtons. The radius is what? 0.02 meters. And it's sine of what? Now, you say, well, now, Mr. Shields, what do we use here? Do we use 90 or do we use, all right, well, yeah, you have to think about it. You have to think about, let's see now, where's the plane that's being pulled through? All right, here's our plane. So from here to here, that's 90, isn't it? That's 90 degrees, isn't it? So it's actually positive 90, isn't it? Okay. And again, you say, how do you know that? Because we're turning counterclockwise. So that's a positive 90 degrees. All right, and then it's plus 30 newtons. Got to do this one over here now, force 2, times 0.02 meters, times the sine of what? Well, now we know that's going clockwise, so that's a negative 90 degrees. Whoop, 90 degrees, okay? All right. And so then our torque net is going to be what? Well, I don't know. Let's do the math. All right, so we've got 20 times 0.02 times sine of, I need to put all that in parentheses too. All right, so we got 20 times 0.02 times sine of positive 90. All right, so 90 plus, do parentheses again, 30 times 0.02 times what? I can't even think. Sine of negative 90. And we get a what? What do we get for our net torque? We get a negative 0.2 Newton meters, don't we? We get a negative 0.2 Newton meters, okay? All right? And no, I know that I've told you when we're looking at work that a Newton times a meter is a joule. Okay, we're not looking at work, okay? We're looking at torque. Okay? We're looking at the force. We are looking at what is required to cause that object to rotate through a given radius, okay? What force is required. We're not looking at work, okay? All right. Okay, so that's number what? 21. I think that's all we had to do. Yeah, so there's your answer. All right, let's look at another one now. Let's look at number 39, still on chapter 7. Okay, number 39. Let's see what we have here. All right, it says a regulation tennis ball is a thin spherical shell of 40 millimeters in diameter with a mass of 2.7 grams. What is the moment of inertia about an axis that passes through its center? So we have a tennis ball here, okay, and it has a diameter. The diameter is what? 40 millimeters, so that's 40 millimeters, which is what? That's going to be what? Well, if it's 40, not 44, 40, goodness gracious, 40 millimeters. All right, so that's going to be what? 40 times 10 to the negative third meters. Is that correct? It's 40 millimeters. Okay, if you're 40 millimeters, move your decimal 1, 2, 3. Okay, so that'll be 40 times 10 to the negative third. Okay, don't forget your prefixes and how to determine. So it'd be 40 times 10 to the negative third meters. Okay, has to be in meters. And then the mass is what? 2.7 grams, which is what? 1, 2, 3. That's going to be 2.7 times 10 to the negative what? 2 kilograms. I think that's right. 1, 2, 3. No, to the negative 4. My bad. Got to be careful now. Yeah, 1, 2, 3. Yeah. So it'd be, put your decimal here, to be 1, 2, 3. Oh, Lord of mercy. I can't get nothing right today. It's -3, crazy head. There we go. Yeah, because if it's 2.7 grams, it's you divide by 1,000. It'd be 2.7 to the -3 kilograms. Yeah. All right. Now let's look at the moment of inertia. Now, the formula, you say, well, now this is a thin shell, right? We have to look up the formula for the moment of inertia for the thin shell. That's in your textbook. I can't remember exactly what page it's on. Gotta find it. Well, shoot. Oh, I hate it when I can't find something. I guess I should have already had it marked. Yeah, page 226. And it's 2/3 mr squared. So the moment of inertia is 2/3 mr squared, correct? Yep, sure is. Okay, so let's just plug and chug now. Okay, so we got to find the moment of inertia about the axis, through the center of the axis, okay? So we just plug everything in, 2/3. The mass is 2.7 times 10 to the -3 kilograms, times the radius, which is 40 times 10 to the -3 meters, okay? Oh, that's the diameter. Son of a gun, I got to use the radius. I'm fixing to quit, go home. I'm sorry. So the radius then is what? Radius is 20 millimeters, or 20 times 10 to the -3 meters. Okay. All right. So that's going to be yeah. And so what do we get? So we get times, and that's squared, times 2.7 exponent to the -3 times and we should get I did something wrong. I punched the wrong number. Okay, so 2/3 times I'm going to work this thing backwards. There we go. I punched it in wrong. 7.2 times 10 to the -7th, and that's kilograms meters squared, isn't it? Sorry about the boo-boos there. Okay. There's your moment of inertia. Okay. So that's problem number 39. And let's do one more in chapter 7. Problem number 45, and we're on page 240. Okay, so this is page 240. All right. Number 45. Okay. It says a small grinding wheel has a moment of inertia of 4 times 10 to the -5 kilograms meters squared. What net torque must be applied to the wheel for its angular acceleration to be 150 radians per second squared? All right. Well, we also know we can calculate torque. And again, these are equations that I go over in the videos, lecture videos, and is also in your textbook. I think it's equation 7.21 if you want to go look in your book. that torque is equal to the moment of inertia times the angular acceleration, okay? So we want to know then what the net torque would be. Well, that's real easy, y'all. So then the torque is going to be, the moment of inertia was what? 4 times 10 to the negative 5th kilograms meters squared, okay? And then the angular acceleration was 150 radians per second squared. And so we get a net torque of what? Let's do that real quick. So 4 to the negative 5th times 150. And we should get 6 to the negative 3rd Newton meters. Okay? So those are fairly simple calculations. All right, I'm going to pause before the next chapter, and then we'll come back. Okay, so now let's do chapter 8. And let's look at number 1. So chapter 8 is pages 266 to 268. Pages we're going to be working on. I don't know what it is about coming over here close to that edge on the left, but don't want to write. Number 1. All right, so we have a 64 kilogram student stands on a very high rigid board that sets on a bathroom scale at each end, as shown in figure 8.1. What is the reading on each of the scales? Okay, so we got a scale here, and we got a board, and we got a scale here. So this is a scale, and we got a person, and the person is standing right here. And from here to here is a distance of about, a length of about 1.5 meters, or a radius, I guess you could say, of 1.5 meters. So from here to here, there to there, okay, is 1.5 meters. Okay, that's where they're standing. So we want to know what the reading is on the scale. So the mass of the student is 64 kilograms. We know that gravity is going to exist, 9.8 meters per second squared. So what would the weight of the student be? Well, the weight of the student would be 64 kilograms times 9.8 meters per second squared. And what do we get for a weight, which, by the way, is a force? So we get 64 times 9.8. That's 672.2. Did I do that right? 64? Yeah. So that's 672.2 newtons is the weight of the student. Okay, that's the student's weight. All right, so what are we looking at here? We got to find actually what we're looking at is the torque, or the sum of all torques. Well, we know that the sum of all torques is equal to what? All right. Well, it's actually going to be the torques. It's going to be the torque 1 plus torque 2, isn't it? Oop. Torque 2, okay. All right, so let's look at what we got. So the question is, we want to find what the sum of the torque is on the right side scale. Is that correct? I think it would be, okay. All right. But now, hang on a minute. We've got to also remember something else. We've got to remember what kind of torque is being created. All right, well, weight is in this direction, right? So pushing down on this scale, okay, the board is going to actually go which way? It's actually going to go this way, isn't it? Yeah, because see, here's the force. The board is going to tip that way. So that is actually a what? On this side, torque is positive. On this side, it's going to go that way, isn't it? Okay, now think about the center. Think about the board coming up this way. Here, the board going that way. Well, this is going to be a negative torque, right? It's going to be a negative torque. Okay, now the length of the board is 2 meters. I forgot to write that down. So the board length, oh shoot, I'm just going to write it right here. Board length is 2 meters, okay? So from there, from the length of the board is 2 meters. Okay, so if we take then we want to know what it is on the right side of the scale, right? So what would it be on the right side? In other words, from here to here, which is 2 meters, what would it be? We don't know. So then we have the sum of all torques. Well, we equal to what? Well, we got 2 meters times the unknown torque or force. And by the way, we're going to just say that actually is the normal force too, by the way. So we're going to say force normal minus, you say, why minus? Because look, here the torque is positive because weight's pulling it down this way. Over here on the left-hand side, the torque is negative because if you go from here to here, if you go from here to here where he's standing, the torque is going that way. It's going this way. That's a negative torque. That's clockwise. So it's minus, and the distance is 1.5 times the weight, which was 6. Did I do that calculation right? Let me look at this again. Let me make sure. 64 times 9.8 is 627. I wrote it backwards, y'all. I'm so sorry. I bet y'all were flipping out. 627.2. Yeah. I'm sorry. I wrote it backwards. Lord help. Okay, so that's 627.2 newtons. And so this is on the right-hand side, going the full length of the board. What do we get? All right, well, we do what? We divide, what's 1.5 times 627.2 divided by 2 meters, and we get 470.4. So this answer is 470.4 Newton meters, right? And that's on the right-hand side, right? Okay, that's over here. It's going the full length of the board, okay? All right, because look, you solve for here, you add this to both sides, divide by 2, and see that makes it positive. So we have 470.4 Newton meters, okay, on the right-hand side of the scale. You say, how can that be? Well, the weight's here, the board's going to go that way. It's going to be positive. See, the weight's here, tips it up that way. All right. Okay. Now, what about on the left-hand side? Well, basically what that is we can find the left-hand side by taking the weight from here to here and subtracting it. So we got what? We got, so the torque then, and it was asking for force, not Newton meters. I'm sorry. What does the scale read? Not torque. It's asking for force. And torque on the brain. Force on the right-hand side. There we go. Okay, the meters cancel out. My bad. All right, so we're looking for the force on the right-hand side, or left-hand side, so on the left. Well, we take what? We take the 627.2 minus 470.4, and what do we get? Well, we get 627.2 minus 470.4, and we get 156.8 newtons, okay? So there it is on the right hand and on the left hand side. That's what the force would be, okay? So that's number 1. All right, so now let's look at number what? What are we doing next? Number 25? Yeah. All right, number 20. Yeah, number 25. All right, it says on one end, so the number's still on chapter 8, okay? On one end, that's, by the way, that's page 267, okay? All right, on one end of a 10 centimeter long spring is attached to the ceiling, so we got a ceiling up here, and we got a spring. Let's see if I can draw a spring, okay? And the spring is 10 centimeters long. This is 10 centimeters, which is 0.1 meters. So that's the length of the spring. So you might say that's X, okay? All right. X initial, okay? And then it's attached, let's see, when a 2 kilogram mass is hung from the other end, the spring stretched to a length of 15 centimeters. So if we come in here and redraw it, all right, mass is 2 kilograms. Now the length goes to what? 15 centimeters, which is equal to 0.15 meters, okay? So it stretches out. What is the spring constant? Okay, what is the spring constant? Well, we know, now what, first of all, let's look at something. And I put X, I should have said Y. I'm sorry, because it's straight up and down. My bad. It's actually Y. So this is Y initial, and this is Y final, okay? So what's delta Y? Well, delta Y is equal to Y final minus Y initial. So we got 0.15 meters minus 0.1 meters gives you 0.05 meters, right? Okay. Okay. Then we can find the spring constant. Well, we know that the force on a spring is equal to what? Negative K change in Y, right? Negative K change in Y. Now remember, the negative is the only thing it's telling us is that it is the restoring force, okay? It is the restoring force. Okay? So we need to find K, do we not? All right. So K then is equal to the force applied to the spring divided by the change in Y. And by the way, the force applied to the spring can be equal to mg. So K, and you say, well, where does that negative go? Okay, y'all, look. If you distribute the negative through right here, when you get the equation, did I write that equation right? Yes, I did. Okay. If you distribute the negative through, you'll see that it becomes positive. All right. But remember what I said in lecture. That really only tells us that the restoring force is in the opposite direction. Okay. So don't get all snafu'd up on the negative. All right. All right. So we have then what? We got the mass, which is 2 kilograms, times 9.8 meters per second squared, divided by the change was what? 0.05 meters. And so what do we get for a spring constant? We got 2 times 9.8 divided by 0.05. And we should get 392 newtons per meter. So that's K, and that's A, by the way. Right? Yeah, that's A. And then it says B, 25B, it says on one end of the, all right, it says how long is a spring when a 3 kilogram mass is suspended from it? Okay, so now we want to find the change in Y, don't we? All right, well, we want to know how long is it if you hang a 3 kilogram mass? Okay. All right, well, we know that the force on a spring is equal to negative K times the change in Y. All right. So if it goes out, so if we take the spring and we stretch it out, what is this? What is Y? Okay? Question mark. Oh, all right. Well, let's see what it is then. Well, we know then that the delta Y is equal to what? The force of the spring divided by negative K, or we'll just say K, because remember, all that tells us is the restoring force. Okay? All right, so we know that is equal to mg. So We've got 3 kilograms times what? 9.8 meters per second squared divided by, what was the spring constant? I said it was 390, what was it? 392? 392, yeah. Newton meters. And so what do we get for a delta Y? All right, so we got 3 times 9.8 divided by 392. And what do we get? We get 0.175. No, wait a minute. Yeah, we get 0.075 meters. That's delta, isn't it? So that's the change in the spring. Right? That's change in the spring. However, we want to know what its final length would be. Well, so we're looking for final. So let's write it this way. Y final, and that should be a negative because this is negative. Okay. So Y final minus Y initial, again, y'all, you do have to remember that when you do one of these, okay, is equal to what? Change in Y, isn't it? So let's find here. So we got change in Y. So Y final is going to be equal to what? Delta Y is equal to what? Oh, dang it. Y final plus Y initial. Okay. Did I write that right? Hang on just a minute. Let me think about it. Yes. All right, let me think. Yes. Well, no, I said that was negative, isn't it? You're not going to subtract the two numbers. You got to add the two numbers together. So I should have just left it alone. That's right. Now, so we got 0.075 plus, what was the initial length of the spring? 0.1 meters. And so we get a Y final of 0.175 meters, correct? Correct. Now, would that actually be negative? Well, it all depends. I mean, in actuality, if you look at how this is hanging, that is in the negative direction. So if you put in 0.175 meters and it gives you it tells you the sign is wrong, then go back and put in a negative. If it was me, if I was asking you to work this problem, I would just have you on a test in my classroom. I would just say, look, that's what it is. And we know that it's in downward. Okay, we know it's downward. So you could say 0.0175 downward. Okay? Okay, so let's not get too snafu'd on that. So if it counts you wrong for putting positive on the Mastering Physics, go back and put a negative, because you get 3 chances per answer, okay? Or per question. All right, that's number 25. How many more we got to do? 2 more? Okay. Let's look at number 33. Okay, still on chapter 8, number 33. Or is this the last one? Have I skipped one? No, I haven't skipped one. Okay. All right, so number 33, chapter 8, says, what hanging mass will stretch a 2 meter long, 0.5 millimeter diameter steel wire by 1 millimeter, okay? So, we got a wire and we got a mass, which is unknown. Mass is unknown. All right, so the length of the wire from here to here is 2 meters. That's L. Okay. That's from here to here. Okay, 2 meters long. All right, the diameter of the wire. So the diameter of the wire is, what did I say it was? 0.5 millimeters, which is what? 0.5 times 10 to the negative third meters. Or you could say 5 times 10 to the negative fourth meters. You could do it that way. All right. And let's see. And we're going to stretch it to the change in L, so delta L, is going to be 1 times 10 to the negative third meters, okay, because it says 1 millimeter, okay? All right. So we want, the change in length is that. So we know this is going to be a Young's modulus equation, right? We know it's going to be a Young's modulus. And we know that Young's modulus is what? Well, we know that Young's modulus is equal to the force times the area. In this case, force is weight. Force times the area, or excuse me, force divided by the area. 1 second. Yeah. Force divided by the area. Force divided by the area over delta L over L. Okay? Okay. All right. So now we want to rewrite our equation and solve it for mass. Okay? So if we rewrite the equation, and where's mass? Well, here's mg right here. If we write the equation and solve it for mass, it is m is equal to, the area, of course, is going to be what? Pi r squared times what? Times y times the change in L divided by g times the original length. That's what your final equation. You say, goodness gracious, all right, you just got to not flip out and look at what you got here. You got a series of complex fractions. See, this could actually have been written mg over a and delta L over L, which it is. You got a complex fraction, you solve for m, well, that's what it looks like. What is this right here? That's area. That's the area, cross-sectional area of the wire, okay? So we got m is equal to, and you use pi, by the way, pi times, what's the radius? The radius, if the diameter is 0.5, then the radius is 0.25 times 10 to the negative third meters. Everything's got to be in meters. All right, the Young's modulus, you have to look this up in the textbook. The Young's modulus is 20 times 10 to the 10th, and that's in the textbook. Oh, what page is that on? Yeah, it's on page 255, table 8.1, all right? So we got 20 times 10 to the 10th, and that's what? Newton per meter squared, Newton per meter squared. That's Young's modulus for the steel. Times what? The change in length was 1 times 10 to the negative third meters, all divided by 9.8 meters per second squared times the length, and the length was 2 meters. And so then the mass is going to be equal to what? We should get 2 kilograms. 2 kilograms, okay? We should get that or real close to it, okay? It's 2 kilograms, okay? All right, that's a really good problem there. And then let's look at the last one, number 41. And number 41 is still on page 268. And so we have one more here. It says we have a glass optical fiber in a communication system has a diameter of 9 micrometers, and that's 10 to the negative 6 meters. So we have an optical fiber, okay, and it has a diameter. A diameter is 9 micrometers, which makes the radius what? 4.5 micrometers. Okay, is that right? Yeah, 4.5 micrometers if we were to need the radius. All right, and we will. And then it says what? What maximum tension could this fiber support without breaking? So A, basically what we're looking for is what? The tensile strength. The tensile strength, right? So how do we find that? Well, the tensile strength, so we do what? So we do the tensile strength times what? Times the area, right? To find the tensile strength. Okay? And you say, how do you get that? Well, stress is defined this way. The force divided by the area. Okay? So we want to find the tensile strength, and the stress is Young's modulus, okay? All right, so here we go. So F, which is tensile strength, is equal to 60, the tensile strength of the optical fiber, and that's on that page I told you a minute ago, times 10 to the what? 10 to the 6 newtons per meter squared. All right, and then area is what? Well, that's going to be pi times 4.5 times 10 to the negative 6. Negative 6 is micrometers squared. And so then the force is what? Well, let's do the math. And we get 3.82 to the negative third newtons. Or 3.82 millinewtons. Okay, that's A. Now let's look at B. Okay, so B, we want to find what? Assume that the fiber stretches in a linear fashion until the instant it breaks. By how much will a 10-meter long fiber have stretched when it is at the breaking point? Okay. So if we remember then the equation for Young's modulus, we remember that equation. So in other words, what are we looking for? So 41B, we are looking for delta L, aren't we? Question mark, all right? Well, if you remember the equation for Young's modulus, we just wrote it down just a second ago. Okay. Let me rewrite it. All right, so Young's modulus is equal to what? The force divided by the area divided by the change in length divided by the length. Got a complex fraction, so we're going to solve for delta L. So delta L then, if you plug everything in and solve, is going to give you what? The length times the force divided by the area times Young's modulus. So that's a complex fraction, so do all the math and you'll get it, okay? Okay. So delta L then, let's plug everything in. All right, the length was what? 10 meters. The force was what? Was it 3.82 times 10 to the negative third newtons divided by, I believe that's right, wasn't it? Yeah, okay. The Young's modulus was what? Or excuse me, the area was pi times 4.5 times 10 to the negative sixth meters squared times what? All right, assume that the fiber, yeah. So that is, it's what? It's 60, right? It is 60, correct? No, I'm sorry. It's a glass fiber. Yeah, I picked the wrong number a minute ago, didn't I? It's 7. It is 7 times 10 to the what? 7 times 10 to the 10th newtons per meter squared. Okay. All right, so let's do all that crazy arithmetic. And what do we get? We get a change in length approximately or very close to 8.6 times 10 to the negative third meters. Let's double check that math there real fast. Times 3.82 negative third divided by, okay, forgot to square that right there too. Sorry about that. I'm here, y'all. I'm just punching the calculator, making sure I get all my functions in. Yeah, 8.57, I get 8.58 times 10 to the negative, what did we say it was? Should have been a negative third, yeah. Okay. All right, and that's it for this chapter. I'm going to pause and get set up again. Okay, students, let's go to the next chapter, chapter 9, and pages 303 to 305. Okay, let's look at number 5. We got a student throws a 120-gram snowball at 7.5 meters per second at the side of a schoolhouse where it hits and sticks. Okay. All right, so we got a student and he's throwing a snowball. Here's the schoolhouse. Okay. Door. He throws a snowball and it hits and sticks right there, okay? And so the initial velocity of the snowball in that direction is what? 7.5 meters per second, okay? The mass of the snowball is 120 grams, which is actually 0.12 kilograms. All right? The final velocity of the snowball, and that's the snowball, the final velocity of the snowball is 0 meters per second. Because it sticks. What is the magnitude of the average force on the wall if the duration of the collision is 0.15 seconds? So we want to know force average, okay, the question mark, and the duration of the contact is 0.15 seconds, okay? All right. Well, this is pretty easy. This is not hard. All right. So we want to find the force average. That's the duration of contact, duration. Well, this is an impulse problem. You say, how do you know that? Well, for one, it talks about speed and it gives you a time, and then it asks about average force. And so we know that the average force in an impulse is equal to what? The change in momentum divided by the change in time, correct? Okay. Because how do we define impulse? Well, impulse is defined as what? J, or delta P, is equal to the average force times delta, excuse me. I'm sorry. So dry electric heat. Okay. Okay, we know that by definition. That's the definition for impulse. That's how we solve impulse. And by the way, that can also be delta P. Change in momentum is impulse. Okay, so how do we do the change in momentum? Well, we have an initial velocity, we have a final velocity. So the final velocity is 0 meters per second times the mass, 0.12, which is 0, minus, well, let's see, its velocity was what? Initial velocity was 7.5 meters per second times 0.12 kilograms. And then divide all that by 0.15 seconds. And so what do we get? We get a negative okay, hang on. Divided by 0.15. We get a negative 6. So the average force is negative 6 newtons. Okay. Now, again, listen to what that says. What is the magnitude of the average force? It actually asks for magnitude, so we'd make it positive, wouldn't we? Yeah. So it asks for magnitude be 6 newtons. I overlooked that. Magnitude of the average force on the wall if the duration of the collision is 0.15 seconds, okay? All right, and that's what it would be, 6 newtons, because it did ask for magnitude, okay? All right, hopefully that makes sense. All right, now let's look at number 21 on chapter 9. Boy, I don't know what's going on with my writing today. There we go. Number 21. All right, so we got a 2.7 kilogram block. Okay. And the mass is 2.7 kilograms of wood. Sets on a frictionless table. Okay. All right. A 3 kilogram bullet is fired horizontally at a speed of 500 meters per second. So we got a bullet that is fired, that's a bullet, and the velocity of the block, initial velocity, is 0 meters per second because it's sitting still. All right, the velocity of the bullet initially is what? Well, it's fired at it at a speed of 500 meters per second. Okay, that's the velocity of the bullet initial. Okay, that's the bullet. Oh yeah, what was the mass of the bullet? A 30-gram bullet. And so the mass of the bullet is 30 grams, which is equal to 0.03 kilograms, okay? 0.03 kilograms, okay? All right, good. Goes completely through the block, emerging at a speed of 220. So the velocity of the bullet, final bullet velocity, is 220 meters per second. Okay. What is the speed of the block immediately after the bullet exists? All right, so we want to know, and that's the block, and the velocity of the block final is equal to question mark. So we want to find the velocity of the block after the bullet hits the block and goes through the block. Okay, well this is simply a conservation of momentum problem. Okay, that's all this really is conservation of momentum. Okay. So in other words, this is P initial is equal to P final, correct? Because momentum is conserved, and if you say P final minus P initial, you get 0, don't you? Because momentum is conserved. So P final is equal to P initial. So how do we write that? So we got the mass of the block times the velocity of the block initial plus the mass of the bullet times the velocity of the bullet initial is equal to the mass of the block final times the velocity of the block final plus the mass of the bullet final times the velocity of the bullet. Actually, the mass is not changing. I could leave that final off there. Okay, so it's a huge equation, isn't it? Does everybody see how that is? So we want to find then the what? We want to find the velocity of the block final. Okay? So what does our equation end up looking like? Looks like a bunch of horrific arithmetic, doesn't it? No, not really. Not really. Okay? So we could write it this way. We could solve for this right. I should have said block, BL. I forgot they're both bullet and block. Okay. All right. So we could solve for right here, the velocity of the block final, by doing what? By subtracting this quantity from this side of the equation and divide by the mass, couldn't we? Is that correct? Should be. It should work out that way. Does everybody see that? I'm giving y'all just a little bit of time to look at it. Yeah. So then we would say the velocity final of the block, BL, is equal to MB VB initial plus MV BL initial minus MB VB final divided by the mass of the block, right? Is that right? Did I do my math right? I believe I did, because we're looking for the final velocity of the block. Yeah. Mm-hmm. All right, so let's plug everything in. Velocity final of the block. All right, so we got the mass of the bullet, which is what? So we got 0.03 kilograms times what? 500 meters per second, plus the mass of the block, which was 2 kilograms, times 0. All right? Okay. Minus the mass of the what? Bullet, which is kilograms, times the final velocity, which was 220. All divided by the mass of the block, which is what? 2 kilograms? Why did I say 2? It's 2.7. There we go. Okay. Now, let's see if we can do all this crazy arithmetic. Okay. I'm going to pause it a minute because I got a lot of punching to do. Okay, y'all. I made another boo-boo. Y'all, I'm sorry. That is 0.003 kilograms. Add another 0 in here, add another 0 in there, and we get an answer of 0.31 meters per second. Okay? I should have just said 3 times 10 to the negative 3 is what I should have said. Okay? Sorry about that. Everybody catch that? All right, because you move the decimal 3 places to the left. Okay? All right. That's a good problem. Okay? That was number what? That was number 21. Yeah. Let's look at number 27 now. Okay, we got a 300 gram bird flying along at 6 meters per second. So we got a bird. Lord, I don't know if I can draw this. All right, we got a bird flying here. Okay, and the bird's initial velocity is what? 6 meters per second. The mass of the bird is 300 grams, which is equal to, move the decimal 3 places, 0.3 kilograms. Okay? All right? Okay. And what does it do? It sees a 10-gram insect headed right for it. So here's the insect. All right? Headed right for it. And the insect, the mass of the insect is 10 grams, which is what? 1, 2, 3, 0.01 kilograms. Okay. And its velocity of the insect, initial velocity of the, and this is the bird and this is the insect, is what? 30 meters per second. And by the way, which way is it flying? Well, the insect is flying this way and the bird flying that way. Correct? So that should be negative 30 meters per second. Right? Okay. And by the way, that previous problem was a elastic collision. Okay. This is an inelastic collision. You say, well, how do we know that? Well, let's keep reading. The bird opens his mouth wide and enjoys a nice lunch. What is the bird's speed immediately after swallowing? So we want to find the final velocity of the bird. This is an inelastic collision. Okay? Inelastic collision. Why? Because the insect completely stops. It becomes stuck to the bird's belly. Okay? They stick together and the bird keeps going right along. Okay? But it does slow the bird down just a little bit. Okay? All right, so how would we write this equation? How would we write this? Well, we know that the momentum initial is equal to momentum final. Okay, so what is the initial momentum? Well, we have the mass of the bird times the velocity of the bird initial plus the mass of the insect times the velocity of the insect initial is equal to, what is the final situation? Well, they become one, don't they? So the final velocity of the system, of the bird-bug system, is equal to what? Well, the mass of the bird plus the mass of the insect, right? Okay? Everybody with me on that? Okay, so final velocity of the bird insect, we're going to call it the entire system, is equal to what? The mass of the bird times the velocity of the bird initial plus the mass of the insect times the velocity of the insect initial divided by the mass of the bird plus the mass of the insect. So let's plug everything in. So the velocity of the system final velocity final, is equal to what? The mass of the bird was 0.3 kilograms times what? It was moving along at 6 meters per second, plus the mass of the insect is 0.01 kilograms times negative 30 meters per second divided by 0.3 kilograms plus 0.01 kilograms. And so what do we get for a final answer? Okay, this is a good inelastic calculation. All right, so let's see. I'm going to pause it while I calculate because I don't want to just kill time y'all hearing me punch a calculator. Okay, so the answer to that then is what? Oh, one other thing too. Y'all didn't catch me on this, I bet, or maybe you did and you're screaming at me through the computer screen. The final velocity of the insect is 0 because it stops in the bird's belly. So we get an answer of 4.84, don't we? 4.84 meters per second. So the bird slows down a little bit. Now, does that make physical sense? Of course it does. Think about it, because the bird was flying along at 30 meters per second in the opposite direction. So it's going to slow the bird down just a little bit, okay? Okay? All right. Hope this helps on that one. All right, now let's look at one more. Number 40. Okay. Okay, so number 40 then is not too bad. It says, what is the angular momentum about the axle of a 500-gram rotating bar in figure P 9.40? Okay, so, and this is on page 305, chapter 9. All right, so we got a bar, okay. There's the center of the bar. The bar has a length of 2 meters, okay. Well, the length is 2 meters, all right. And it has a revolutions per minute, and it's rotating that way, 120 revolutions per minute, right? RPM. So what is the angular momentum? We want to know what the angular momentum is, okay? So how do we find that? Well, the first thing we need to do, well, we know that angular momentum L, and I probably shouldn't have written the big capital L there because that's not angular momentum. Let's just say the length, little l, the length is 2 meters. Angular momentum L is found by doing what? Angular momentum can be found by taking the moment of inertia times the angular speed, okay? Well, we got to find the angular speed, don't we? Well, angular speed can be found simply by doing what? Angular speed can be found by taking 120 RPMs, revolutions per minute. All right, that's 120 times what? Well, we know that 2 pi radians, okay, we got to get it into radians, over 60 radians per second because it's in minutes, not hours, okay, not seconds. Because we know that 2 pi radians is 1 revolution, isn't it? So it's making 120 revolutions per minute, okay? And so we come to a, what? We come to 2 times 120 is what? 2 times 120 is what? 240, and 240 divided by 60 is what? 4 pi radians per second? Yeah. So we could write it this way. That'd be 4 pi radians per second. And why did I do this 60 radians per second? Because it's revolutions per minute. I've got to get the minutes into seconds. So it's 4 pi radians. If you want to go ahead and multiply 4 times pi, so that'd be what? So it'd be 4 times, and you got to use the pi key on your calculator. Nah, pooey. 4 times pi. That's about 12.57 radians per second if you want to go ahead and calculate it out. Okay. Either way, it doesn't matter. Okay. We can go ahead and calculate it out. We'll do it here in a minute anyway. So now we can find the angular momentum. So that's going to be what? Well, now the moment of inertia of a rod, and by the way, this is a rod. If you go back to the page where I told you earlier, look up the moment of inertia for various objects based on where the axis of rotation was. This is the moment of inertia of a rod with the axis at the center. That is 1/12, okay, times the mass times the radius squared, right? So that's 1/12 m, or the length, we'll say little l, squared, okay? All right, then times what? Times the angular speed. So 1/12 times the mass, which was what? It told us that it was 500 grams. I forgot to write that down. So that's 500 grams, which is 0.5 kilograms. So we got 0.5 kilograms times what? The length squared, which is 2 meters squared, right? Times 4 pi radians per second, right? Okay, so let's do the math for that real quick. So we got 1/12 times 0.5 times 4 times 4 times pi. And we get what? We get this is what I get, 2.09, and that's going to be what? Kilograms, meters per second, kilograms, meters squared per second, kilograms, meters squared per second. Or we could just say 2.1 kilograms, meters squared per second, okay? All right, and that would be the angular momentum. Okay? And that is it for chapters 7, 8, and 9. I hope this helps.